Hey folks, all right, in this video we start to get to the meat of what we're using Gauss's law for. All right, and generally speaking, we usually try to use Gauss's law to calculate the electric field created by different charges. Now, we've already talked about constant electric fields, and we've talked about electric fields created by point charges. And that's what I want to start with. So let's say we had a point charge right here, and we'll make them. We're going to make all our charges positive. If we had a negative charge, the field will just point the opposite way, but it'd be the same function. And we're going to imagine this makes an electric field outward, like so. Okay, and I want to know what's the strength of that field at different locations. Now, we already know this answer, right? So I'm going to write that down off to the right here. We already know the answer. For a point charge, the electric field is simply kq over r squared. Well, we're going to use Gauss's law to derive this. Gauss's law says that the total flux leaving an enclosed volume which is equal to E dot dA, okay, equals the charge you've captured inside that volume over epsilon naught. Now again, let me repeat the whole double integral thing. We're talking about a volume, and the circle here, we're talking about a surface that encloses a volume. So we have two integrals because it's a surface, and so it's got two dimensions. And the circle means you're enclosing that volume. In other words, it's a surface that envelops a volume. Now, and then the Qn on the right side, that is the amount of charge that's inside of your volume. Now, when you do Gauss's law, here's what you want to do. You don't want to integrate if you can help it. You just want to do some algebra. So you want to create a Gaussian surface that has the following two properties. Property one, the electric field strength is same everywhere along surface or zero. Okay, and then we're going to do a whole bunch of examples, and in those examples we're going to try to pick Gaussian shapes where the electric field strength is the same everywhere or the electric field strength is zero. And the second property you want to try to, well, for what a good Gaussian surface follows, is that the electric field is perpendicular to the area at all points, or parallel to the area vector at all points. Okay, so looking at our example for a point charge, okay, what surface could I draw around the point charge such that the electric field would be the same everywhere along that surface and would be perpendicular to the surface at all points? Well, that's really simple. You're going to draw a sphere that surrounds the charge. And the idea is the electric field is perpendicular to that surface at all points. And if I draw that sphere concentric with the charge, in other words, a charge being at the dead center of the sphere, the electric field strength will be the same everywhere along that green sphere that I drew. If you do that, if you select your proper Gaussian surface, you no longer have to actually do any dot product or integration. This just becomes E times the area of that sphere equals Qn over epsilon naught. Now, there are times when you are going to have to integrate, but oftentimes you don't if you pick the right Gaussian surface. Now, for us, we've got E. What's the surface area of a sphere? Well, that's 4 pi r squared, and then that's going to equal Qn. So how much of this point charge is inside that green sphere? Well, all of it. So I'm just going to call it Q, okay, over epsilon naught. And then you get the following equation. You get E equals Q over, and I'm going to kind of write this in a specific order. You get 4 pi epsilon naught r squared. You might be like, well, wait a minute, Mashar, I thought you said we were supposed to get kq over r squared for our electric field. Well, you might recall that k is equal to 1 over 4 pi epsilon naught. So if I take my 1 over 4 pi epsilon naught out and put a K in, you get the electric field for a point charge is KQ over R squared. Okay. All right, so here's what I'm going to do. I'm going to end that video there. I'm going to actually do the ball of charge on the next video. Okay. Again, when you're using Gauss's law, you're trying to find a surface that is perpendicular to the field at all points and where the field's strength is the same everywhere along that surface. If you do that, you don't have to do a dot product anymore, nor do you have to integrate. It just becomes an algebraic expression at that point. All right, so we got a lot more examples to come. See you in the next one.